Good day everyone, welcome back. So our topic today is a continuation for the semiconductor diode, discussing the energy levels of such devices. So today we will be discussing we will recall some isolated atomic structure of different materials, and note that um, the atomic structure, there are discrete energy levels associated with each orbiting electron for each material. In fact, it has its own set of permissible energy levels for the electrons in its atomic structure. Okay? So now we will be looking at an atomic structure of a sodium. Okay? So I hope you can recall your chemistry or physics class. So do you know what is the role of these valence electrons here? Do you know that it has a uh, great role in identifying of what the material is? Is it a good conductor, a non-conductor, or a semiconductor? So as we go through, you will know how these valence electrons determine its conductivity. So first thing first, let me introduce you the valence shell. So what is a valence shell? A valence shell is the outermost shell, and it contains the outermost electrons. And the outermost electrons are called the valence electrons. So for sodium, you know that sodium is a metal, right? So meaning good conductor siya. Why? Because of this single electron it has. So tungod kay isa ra na siya nga electron, dali ra siya maka move. So a good gauge of conductivity is the flow of electrons itself. Since dali ra ni siya maka-move kay di na siya kinahanglan og dako nga energy para maka-move siya, it is considered as good conductor. And why it is also considered as good conductor? Because of this. It is belong to the conduction band. These valence electrons are in the conduction band. Conduction band is the band of electrons orbital that electrons can jump into from valence band when excited. When the electrons are in this orbital, they have energy to move freely in the material, as I have said earlier. So since in later, I will show you some figures or pictures na ang valence band o ang conduction band for the conductor nag-overlap lang. While for the insulator, let us look how it differs from the insulator. So let us have an example here of a chlorine atomic structure. So for the chlorine atomic structure, the valence, so let me recall the valence shell and conduction band here. And let us take a look for this atomic structure. We know that for chlorine, we have 17 electrons itself, okay? So given it has 17 electrons, so what we have left for the valence shell is 7 electrons. We have 7 valence electrons. So sa inyong na-observe, diba, mas daghan ang electron sa valence shell. This means na mas solid ang iyahang bond towards that atomic structure. Dili siya basta-basta maka-move freely. So it is closely tied Mura na siya og, okay, let me have an example of typical Filipino uh, material we have in our household. Okay. So we have this broom, right? Natay common saying na kung mas daghan, mas kusgan. So mura po na siya atomic structure sa electron sa atong atomic structure sa insulator. Kay tungod kay mas daghan sila na guard, mas kusgan siya. Dili siya basta-basta makagawas. So, mo na siya ang analogy niya. And also, para makaambak ni, kay dili man, lahi man ang valence band or valence shell o conduction band sa electron, naa siya'y kinahanglan nga isatisfy para makaadto siya to jump into the conduction band. So, that is the forbidden gap. Para makagawas ni siya, para makagawas ning kining electron dere, para makaambak ni siya dere, kinahanglan ni siya og energy gap nga isatisfy or an electron volt energy gap nga isatisfy. And that is called the forbidden gap. Kini siya, kini dere kini nga gap in between is called the forbidden gap or energy gap to satisfy para makaambak sa conduction band. But sadly to say, it is very hard for the non-conductors to jump into the conduction band because it needed bigger electron volts para maka-ato siya sa conduction band. So, okay, that's it. And for the semiconductor, trivia also. Note that sa akong gingon ganina nga, ang valence shell, ang valence electrons could determine the conductivity of material. So note that mostly of the metals or good conductors have lesser valence electrons, like for example 1. And for semiconductors like silicon, they have 4 valence electrons. And for the non-conductors or non-metals, they have greater than 4 valence electrons. Let's say for example 7 or 8. So that is a trivia also. Kung mas daghan ang iyahang valence electrons, mas less iyang conductivity, meaning towards siya sa non-metal or insulator. Okay? So again, let me show you here some figures to illustrate the claims or to validate our claims earlier that there are certain electron volts or the energy gap to satisfy in order for these valence electrons to move or to jump into conduction band. In here, for example, for the insulator needed an energy gap that is greater than 5 electron volts in order for this valence electron to move to the conduction band. While for the semiconductor, we have different values of energy gap to satisfy. For example, we have this silicon of 1.1 electron volt, and for germanium we have 0.67 electron volt, and for the gallium arsenide 1.41 electron volt. With this, certain values of electron volts calls for different application. You may search in Google or any book, or you can read this application of these certain materials because of these different values of energy gap. So, and also take note that germanium has the least of the energy gap to satisfy. And for the conductor, as I have said earlier, this conduction band and valence band just overlap itself, so there's no need of electron volt or energy gap to satisfy because they have that energy state already, that they are in the conduction or in the conduction mode. Also, take note that the energy associated with each electron is measured in electron volts here. So the unit of measure is EV. So as defined from defining equation of V is equal to work or the energy over the charge. So the charge Q is the charge associated with a single electron. So substituting this of charge of electron and potential difference of 1 volt, then we will result into an energy level referred to as 1 electron volt, which is just equal to 1.6 times 10 to the power of negative 19 joules. Okay, so that is how we derive it.